My name is Nicolas Menet, and I'm excited to share with you our most recent work on Thompson sampling via fine-tuning of large language models. Bayesian optimization is a powerful framework for optimizing expensive black box reward functions that can only be evaluated pointwise. It balances exploration and exploitation by maximizing an acquisition function derived from a Bayesian belief model. For instance, Thompson sampling, shown here in green, draws the acquisition function directly from the reward posterior and maximizes it to obtain an evaluation location. Because the acquisition function is random, the evaluation locations also end up randomly distributed according to the probability of reward optimality. While acquisition function maximization is tractable in continuous domains via gradient descent, it is fundamentally prohibitive in combinatorial discrete domains such as text, proteins, and quantum circuits, where the number of discrete options exceeds the number of atoms in the observable universe. Instead, we propose to directly parameterize the Thompson sampling policy, that is, the probability of optimality, with a prompt-conditioned pre-trained large language model. Conducting Thompson sampling then becomes as easy as drawing candidates from the large language model, scoring them on the black box reward function, updating the Bayesian surrogate based on the observations, and lastly, fine-tuning the large language model to remain consistent to the posterior probability of optimality, rather than just the prior. To ensure such consistency, we build on variational Bayesian optimistic sampling, which is a variational form of Thompson sampling executed by ensuring the policy maximizes the objective shown here on the screen. First, in our contributions, we derive closed-form gradients to the VBOS objective. Second, as our main theoretical result, we derive a novel cumulative regret bound for VBOS, measuring the rate of convergence of Bayesian optimization. Our novel guarantees improve vastly on the prior art. Now, the regret scales with the maximal information gain rather than the vacuous combinatorially large domain size of prior bounds. The maximal information gain represents the true degrees of freedom that must be explored to reliably find the maximum. That is, our bounds are optimal for Bayesian optimization. Our results also hold for inexact gradient-based VBOS, where we obtain an additional Bregman divergence term that measures how well the VBOS objective was maximized. In fact, our results motivate initialization from strong priors and careful fine-tuning to both accelerate convergence on the VBOS objective and to avoid losing prior knowledge. Experimentally, we validate ToSFiT against numerous baselines on 3 diverse combinatorial domains: text refinement, protein search, and quantum circuit design. The baselines span classical Bayesian optimization, in-context Bayesian optimization, both LLM and non-LLM based evolutionary search, and actor critics from reinforcement learning. ToSFiT obtains state-of-the-art sample efficiency both on small models and on large models. Moreover, ToSFiT can trade off compute efficiency for further sample efficiency gains by conducting multiple steps of gradient descent on the VBOS objective for each round of Bayesian optimization. To conclude, ToSFiT effectively scales Thompson sampling to large unstructured discrete spaces while sidestepping explicit acquisition function maximization. We prove that ToSFiT matches the strong regret bounds of standard GPU-CB and Thompson sampling, with practical lessons on the implementation as well. Empirically, we achieve state-of-the-art sample and computational efficiency across black box optimization tasks that span natural language, biology, and even quantum computing. Thank you for listening.